Okay, one of the viewers sent us this explanation for the tides because we've been very confused about this. And so this is a reference to Classical Mechanics by Taylor.
Let's get into it.
Let's do it. Should we just read it? Yeah, we're figuring it out. The beautiful application of the result of 9.4 is the explanation of the tides. As you probably know, the tides are a result of the bulges of the Earth's oceans caused by the gravitational attraction of the moon and the sun. As the Earth rotates, people on the Earth's surface move past these bulges and experience a rising and falling of the sea's level. It turns out that the most important contributor to this effect is the moon, and to simplify our discussion, I shall, at first, ignore the sun entirely. I shall also assume, at first, that the oceans cover the whole surface of the globe.
Okay.
This
makes sense. Good assumptions to get a feel.
Make it simple. We'll add sun in later, but for now, just work with the moon. This result that the effect of being on an accelerator frame is the same as having an additional gravitational force is the cornerstone of general relativity, where it is called the principle of equivalence. Okay.
Okay. I don't know if we need that for tides, but okay, go ahead.
Thanks, footnote. Okay. We'll come back to this picture. So a plausible sounding, though entirely incorrect, explanation of the tides is illustrated in figure 9.2a. According to this incorrect argument, the moon's attraction pulls the oceans towards the moon, producing a single bulge towards the moon. The trouble, well, let's look at it. So here's 9.28. So you would see the Earth here, the moon, we're spinning around, and the moon pulls the ocean. You get this egg shape.
Yep.
Seems plausible at first.
Okay. Entirely incorrect. I don't know if it's entirely incorrect.
What a jerk. I mean, I guess
there's some intuition there, but it's not entire. It's like 100%. There's nothing you can pull from this argument that works at all.
Brutal.
Like,
I mean, well, I think we'll see that it's half right.
Yeah, it seems to be half right.
Half right. That rounds down to entirely incorrect.
Entirely wrong.
The trouble with this argument, beside that it's wrong, cool little snip, make me feel bad. Okay. I'm here to learn. Is that the single bulge would cause just one high tide per day instead of the observed two. Good. Follow the observation. It's got to be two.
Yeah.
The correct explanation illustrated in figure 9.2b is more complicated. Look at B, there's Earth, Moon, two tides. One on the near side, one on the far side. Perfect. Explanation. The dominant effect of the moon is to give the whole Earth, including the oceans, an acceleration A towards the moon. This acceleration is the centripetal acceleration of the Earth as the moon and the Earth circle around their common center of mass and is almost exactly the same as if all the masses that make up the Earth were concentrated at its center. Some type of Gauss law for mass. I'm okay with that. The centripetal acceleration of any object on Earth and its orbits with the Earth corresponds to the pull of the moon of that object would feel at the Earth's center. Okay, so he's saying we don't have what?
I think this is a far away assumption right here.
I think so.
Meaning the Earth and the moon are far enough away from each other such that the acceleration felt by something on the surface is close enough to the planet is small enough that the acceleration across the whole planet is the same approximately.
And
I think if you start, go ahead.
I think that's right. Like if we were to put this to scale, the moon is like way out there.
The trouble is, I think with the Earth-Moon system is this doesn't necessarily apply because the Earth and the moon are actually pretty close to each other and the Earth is fairly large. So we'll talk about that in a second.
Okay.
But I think this is like, isn't this an Earth and moon are super far apart? And if you're sitting on the surface close to the moon or far away from the moon, your required centripetal acceleration is the same in both cases, approximately. Is that right?
I think that's what he's saying, yeah.
Okay.
Okay, center of the Earth. Here it is. So now any object on the moon on the Earth is being pulled by the moon with a force that is slightly greater than it would be at the center. I think that's right, because the closer you are, the stronger the gravitational force. Therefore, as seen from the Earth, objects on the side nearest to the moon behave as if they felt a slight additional attraction toward the moon. In particular, the ocean surface bulges towards the moon. Right? Seems right. On the other hand, objects on the far side of the moon are pulled away by the moon with a force that is slightly weaker than that it would be at the center of the Earth. which means that they move relative to the Earth as if they were slightly repelled by the moon.
Mm-hmm.
Okay, so I'm okay with that because if we're saying that if you're closer to the moon, you get pulled stronger because the gravitational force behaves like 1 over r squared, so it's stronger pull.
Yeah.
Same thing is true if you're far away, it's a weaker pull. But compared to where you are at the Earth in the middle, that's it's effectively like a push away.
Yep, agreed.
This slight as he says, which means that the Earth relative to the Earth, as if it were slightly repelled by the moon. This slight repulsion causes the ocean to bulge on the side of the moon, that is side away from the moon, and is responsible for the second high tide each day.
Okay.
Cool. I like that.
Cool. I like that.
We can make this argumentative, quantitative, and probably more convincing if we were to return equation 9.4. Okay, we referenced this twice now. Let's look at it.
Mm-hmm.
And 9.4. Okay, if we multiply this equation by m and use 9.1 to replace, by f, we find, okay, let's go a little bit up. So what is this scenario? Consider
So this is relative motion addition.
Mm-hmm.
If we look at that written one right below 9.2,
This one.
ball's velocity relative to ground equals ball's velocity relative to car plus car's velocity relative to ground. So it's like Galilean relativity.
So it's a scenario where you're not standing outside. Okay, it's if you're in a car and you're rolling a ball, and you want to figure out like what is the velocity of the car compared to the ground. Velocity of the ball relative to the ground. You have to add the velocity of the ball in the car plus the car's velocity of the ground. So it's like you add all the things so that way you get a true like bird's eye view.
I think so. And then so 9.3 is you hit the 9.2 with the DDT.
Hit it twice, get the acceleration. And then velocity. Okay,
Oh, you hit it once.
Hit it once. Okay. Okay. If we multiply this equation by m, so that way you get the net force equation, and replace it by r dot squared. R double dot, r not double dot. By f, we find this thing. So this.
Go ahead.
This is equation is exactly the form of Newton's second equation, Newton's second law, except that in addition to the f, the sum of the forces identified in the inertial frame, so that like a bird's eye view, there is an extra term on the right equal to minus m capital A. This means that we can continue to use Newton's second law in the non-inertial f frame S, provided that we agree the non-inertial frame must add an additional force-like term called the inertial force.
Okay, so this is, if I can read this correctly, the m double dot r is your true ma in the inertial frame.
Agreed.
F is your force. Your forces that you see.
Whatever you feel.
Like the real forces.
Yep.
And then the minus m capital A is all the forces due to the car's motion relative to the ground, which look like forces and accelerations to you, but are actually not real.
Right.
Inertial forces.
So to map that onto the Earth, this A, the capital A, is the fact that the Earth isn't stationary. Like the moon is going around the Earth, and the Earth is also getting dragged around a little bit. Like the true center of mass is somewhere here. We've captured that all up in that capital A. Okay, we continue. The forces on any mass m, little m here, near the Earth's surface are 1, the gravitational pull of the Earth, so going straight down to the Earth, I like that.
Yep.
2, the gravitational pull minus gmm d hat over d squared. So that's the gravitational force to the moon.
Yep, makes sense to me.
Oh, of the moon, yeah, it says it. M is the mass of the moon, and d is the position of the object relative to the moon. Yeah, great. And 3, the net non-gravitational force F-ing, or instant, I think, the buoyant force on top of a drop of water in the ocean. Okay, so plus any like, I don't know, there's drag if there's water, if you're a boat and you're floating in the water, then plus the other forces that aren't gravity.
Okay, got it.
Okay. Meanwhile, the acceleration of our origin O at the Earth's center is A is equal to minus gmm d naught hat, or d naught squared. So that's Newton's second law of gravity. So it's this whole Earth is getting pulled in towards the moon, and it's gm d naught at d naught squared.
Yeah, and so it's capital A acceleration, meaning this is going to be the non-inertial acceleration when we're standing on the Earth.
Right.
So this is that, in this next equation, that minus m capital A. That's the thing that's going to go in there.
Okay, perfect.
Okay.
But putting all together, you get the acceleration for a small object is the gravitational force pulling towards the moon, towards the Earth.
Yep.
Thank you. And the gravitational force pulling towards the moon.
Yep.
Any like local stuff like buoyancy, drag, or whatever. Plus, what was this term? This is the acceleration of the entire Earth that you are sitting on.
Yep. So that's the non-inertial acceleration because we're standing on the Earth, going around the moon.
Exactly. Or if we combine the terms with the capital M together, we get the acceleration is equal to gravitational force, the gravity forces, the local forces, and then this FTID. FTID, where the tidal force, we call it the tidal force, which is minus GMM, and then the only difference was these vector quantities right there.
Yep.
It's the difference between the actual force of the moon on M and the corresponding force of M if it was at the center of the Earth. Because if it was the center of the Earth, then this term would be 0. So it's the difference of the two forces. That's straightforward. I like that. The entire effect of the moon on the motion relative to the Earth of any object near the Earth is contained in the tidal force, FTID. At the point directly facing the moon, point P in figure 9.4, P.
Yeah.
Here's the point P.
Yeah.
The vector is D, which is M to P, here of the moon to P, and D naught, M to the center of the Earth, pointed in the same direction, but D, which is here, is less than the long distance. Thus, the first term in 9.12 dominates. What? Okay, so if this is a number divided by small number that's larger than this thing. Okay.
I like how the word dominate means slightly bigger.
Slightly bigger. Dominates. You get a difference in height of 1 meter. Dominates. Yeah. And so then dominates, and the tidal force is towards the moon. Yep. That's right. Yep. Because we get an ocean that rises towards the moon.
Yep.
Dominates. At point R, facing directly away from the moon, again, D equal to the long distance and D naught pointing in the same direction, both going to the right here. But now the long distance, little d, is larger than D naught to the center of the Earth, and the tidal force points away from the moon. Yeah. So if this is now bigger, so then you get a
no, it's not
positive. Let's just say the d is a larger number than D naught, which what?
No, I wasn't correcting you. I was saying it's not bigger. It dominates.
Okay. The net result is that a positive FTID, which is to the right.
Yep.
Cool.
Yeah.
You troll. At the point Q, the vectors MQ and the vector and D naught point in the different directions. Right? So D naught is going to the middle, MQ is going up to this edge here. The x components of the two terms in 9.2 cancel almost exactly, but the first term has a y component because you got to go to the right and up.
Yeah.
Thus at Q, likewise at the bottom, the tidal force is inward towards the center, the Earth's center, as shown here. So that means at P and R you get a stretch out. At Q and S you actually get a contraction in. Like it's not like the oceans stay neutral and only bulge on the outside. Stay neutral. It's like they actually squish in.
Squish in, yeah.
The low tide is not neutral tide. It's actually lower than neutral tide.
Good point. Yeah.
In particular, the effect of tidal force is to distort the ocean in the shape shown in figure 9.2b, the one we got both stretched, with bulges centered on points P and R, giving the observed 2 high tides per day.
Okay. I really like this explanation, but I did have the one question that bothered me. I have 2 questions that bothered me.
Okay.
One was, if we go